In this video, we are going to discuss maxima and minima of z equals f(x,y), where z is a function of two independent variables x and y. If a relation between z and x and y is such that for a pair of real values, say x comma y, we have a unique value of z, then z is said to be a function of two independent variables x and y, which is denoted by z equals f(x,y), where x and y are independent variables and z dependent variable. Hello friends, you are watching YouTube channel Number Collage. This channel features videos on mathematical concepts. Effort has been made to explore the concepts through basic mathematical ideas. Hope you will like my effort. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. If z equals 3x square minus 2y is a function of two variables, and if p is 2 comma 3, then z equals 3 into 2 square minus 2 into 3, which is 6. This may be represented by a line segment p dash of length 6 units. So we have length p dash equals 6. When large number of such points x1 y1, x2 y2, x3 y3, so on and so forth, xn yn are taken for z equals f x comma y, then corresponding values of z, z1, z2, z3, etc., zn can be calculated for each. So a large number of lines such as p dash can be constructed, and in the limit when all the n points are considered, line segments p1 p1 dash, p2 p2 dash, p3 p3 dash, etc., pn pn dash of length z1 z2 z3, so on and so forth, zn will form a surface as shown in the figure. Therefore, the function z equals f(x,y), or in this case 3x square minus 2y, represents a surface and not a curve. Z equals f(x,y) is said to be maximum at a comma b if fab is greater than any point in the immediate vicinity of a comma b. That is, fab is greater than f a plus h comma b plus k for small positive or negative values of h and k. Minima is similarly defined, except that at point a comma b, fab is smaller than at any other point in the immediate vicinity of a comma b. That is, fab is smaller than f a plus h comma b plus k for small positive or negative values of h and k. When a maxima occurs at point a comma b, then the curve lying in the two planes x equals a and y equals b must also have a maximum point a comma b as shown. The tangents t1 and t2 to these curves at a comma b must be parallel to axis ox and oy respectively. Now tangent t1 lies in the plane y equals b, which is parallel to the coordinate plane xoz, and slope of this tangent is given by partial z by partial x equals 0, because y is a constant b, and tangent t2 lies in the plane x equals a parallel to the coordinate plane yoz, and slope of this tangent can be given as dou z by dou y equals 0, because x is a constant a. Now, by solving equations dou z by dou x equals 0 and dou z by dou y equals 0 simultaneously, we get stationary or critical points of z equals fxy. Three types of stationary or critical points are possible: maximum, minimum, and saddle point. To explain in simplistic way, geometrically, we have seen earlier that z equals fxy represents a surface, like a surface here, a surface here, or a surface here. Maximum point on the surface, that is the hilltop here, from which the surface descends or comes down in every direction towards the xy plane. The minimum is the bottom of depression here, from which the surface ascends or climbs up in every direction. In either case, the tangent planes to the surface, this one and this one, at a maximum or minimum point is horizontal, that is parallel to the xy plane and perpendicular to the z-axis. Saddle point is a point where a function is neither maximum nor minimum. At such a point here, the function is maximum in one direction while minimum in another direction. Geometrically, such a surface looks like the leather seat on back of a horse, forming a ridge rising in one direction and falling in another direction. Lagrange's conditions for extrema are nothing but sufficient conditions for extrema, that is for maxima, minima, and saddle point. Before that, let us denote for a function z equals fxy, a function of two independent variables, dou 2z upon dou x square at point a comma b to be fxx at a comma b by r dou 2z upon dou y square at a comma b to be fyy at a comma b by t, and dou 2z by dou x dou y at a comma b to be fxy at a comma b by s. And from these three values we evaluate the quantity rt minus s square, and from whether this quantity rt minus s square is negative, positive, or 0, we decide maxima, minima, and saddle point of function z equals fxy at a comma b. Accordingly, function f attains maximum at a comma b if rt minus s square is positive and r is negative. Number 2, f attains or has minimum at a comma b if rt minus s square is positive and r is also positive. Number 3, f has a saddle point at a comma b if rt minus s square is negative and function f has neither maximum nor minimum. Number 4, there is a failure case if rt minus s square is 0, and in such case further investigation is needed to determine the nature of function fxy. Now we will see how to find maxima, minima, and saddle point of a given function z fxy. Number 1, solve equations fxx equals 0 and fyy equals 0 simultaneously and find critical points or stationary points AB. Number 2, calculate r fxx, s fxy, and t fyy at this critical point a comma b. 3, z is maximum if rt minus s square is positive and r is negative. Then f has maximum at a comma b. B, minimum if rt minus s square is positive and r is positive, then f has minimum at a comma b. See saddle point. If rt minus s square is negative, then f has neither maximum nor minimum at a comma b. And finally D, a failure case if rt minus s square is 0, and in this case further investigation is needed. By following this method, we can find maxima, minima and saddle point of a function z equals f(x, y). In the first example, we have to find maxima minima of function 1 minus x square minus y square. First, let us find fx, which is minus 2x, then fy minus 2y. To find stationary points, we have to equate fx equals 0 and fy equals 0 and solve them simultaneously. That gives us x equals 0 and y equals 0. So 0, 0 gives us the stationary point at which we have to find maxima and minima. Next we find r equals fxx, that will be from here minus 2, which is negative. We name this 1. Next t is fyy, from this it will be minus 2. Next is s fxy, from this it will be 0. Now we have to find rt minus s square, which is minus 2 into minus 2 minus 0 square, that will be 4, and it is positive. We name this 2. rt minus s square is positive, shows that the function has maxima or minima, and r is negative, shows that given function is maximum at stationary point 0, 0, and the maximum value will be 1 minus 0 square minus 0 square, 1. In the second example, we have to find maxima minima of function x square plus y square. First fx 2x, then fy 2y. For stationary point, equating them to 0 gives us x equals 0, y equals 0. So 0, 0 is the stationary point. Next r is fxx 2, which is positive, then t fxy 2 again, s fxy, which is from here 0. Now rt minus s square will be 2 into 2 minus 0, 4, positive, which implies given function has maxima or minima, and since r is positive implies that given function has minima at the origin, and the minimum value of given function will be 0 square plus 0 square, 0. Next function for finding maxima and minima is xy, for which fx is y, fy is x. For finding stationary values, we will equate each of them to 0, so that gives us origin 0, 0 as the stationary point at which maxima or minima could happen. Next is r fxx 0, then t fyy 0, and s fxy. From here it will be 1. Obviously rt minus s square will be 0 minus 1 square minus 1, negative, which implies given function xy has a saddle point at the origin and hence has neither maxima nor minima. Next function 1 minus x square y square. Fx is minus y square into 2x minus 2x y square. Fy minus x square into 2y minus 2x square y. Equating fx equals 0 and fy equals 0, we get x equals 0, y equals 0, which means origin is the stationary point where maxima or minima could happen. Next fxx from here will be minus 2y square. So r at the origin will be minus 2 0 square 0. Fyy from here will be minus 2x square and this at the origin, that is p is minus 2 into 0 square 0, and fxy will be again from here minus 2x into 2y minus 4xy, which at the origin will be s equals minus 4 into 0, 0. So here we got r equals t equals s equals 0. That gives rt minus s square 0, and this implies further investigation needed. Now we have fab equals the function at the stationary points, that is at the origin, 1 minus 0 square into 0 square 1. Let h equals 0.1 and k 0.2 close to the stationary point 0, 0, and evaluate f a plus h p plus k, which will be 1 minus 0.1 square into 0.2 square 1 minus 0.01 into 0.04 1 minus 0.0004. Now we have f a b minus f a plus h p plus k equals this one minus 0.9996 minus 0.9996, that will be 0.0004, which is positive, implies that given function has maxima at the origin 0, 0, and the maximum value will be 1 minus 0, 1. Next we find maxima minima of function x square y square. Fx is y square into 2x, 2xy square. Fy is x square into 2y, 2x square y. For finding stationary values, we will equate fx equals 0, fy equals 0 and solve them simultaneously. That will give us x equals 0, y equals 0. So 0, 0 is the stationary point at which maxima or minima could occur. Next we find fxx, which from here will be 2y square. So r will be 2 into 0 square 0. Fyy from here will be 2x square. So t will be 2 into 0 square 0, and fxy will be again from here 2x into 2y 4xy, and s at the stationary point will be 4 into 0, 0. So here r equals t equals s, which gives us rt minus s square equals 0 minus 0, 0, which implies further investigation needed for finding maxima and minima. FAB will be from here 0 square into 0 square 0. Next we select small values of h and k which are very close to a and b, that is at the origin. So let h equals 0.1 and k equals 0.2. So f of a plus h p plus k will be f of 0.1, 0.2, 0.1 square into 0.2 square, that will be 0.01 into 0.04, 0.0004. Now we will find f of ab minus f of a plus h p plus k, which will be this 0 minus this 0.0004, which will be negative, and that implies given function x square y square has minima at the stationary point 0, 0, and the minimum value will be 0 square into 0 square 0. Now we will solve an example of a perfect saddle point case. Given function is x cube y square. Fx will be y square into 3x square, 3x square y square. Fy will be x cube into 2y, 2x cube y. Equating fx and fy to 0, we get stationary points x equals 0 and y equals 0. So the origin is stationary point where maxima and minima could occur. Next we find fxx from here 3y square into 2x 6xy square, and therefore r at stationary point will be 6 into 0 square 0. Fyy will be from here 2x cube. So t at the stationary point will be 2 into 0 cube 0. Fxy again from here will be 3x square into 2y 6x square y, which at stationary point s will be 6 0 square into 0 0. So we have here r equals t equals s equals 0, implying rt minus s square equals 0, which means further investigation needed. Now f at stationary point will be 0, but because of this cubic term here, for small values h and k in the neighborhood of 0, 0, f a plus h p plus k will be sometimes negative and sometimes positive, which means f a comma b minus f a plus h p plus k will sometimes be positive and sometimes negative. So this is a perfect case of saddle point, which means the function has neither maxima nor minima. Viewers, if you like this video, please click the like button. Share this video with your friends and classmates. Subscribe to this channel. Post your constructive comments to make the videos better. You can even check playlist of this channel. Perhaps you might find videos that you are looking for. See you in the next video. Until then, keep watching Number Collage. Thank you.